Well, welcome everybody. So tonight we're going to be talking about the OpenAI scaling laws paper. Um, I will say this: the kind of the concept for scaling law seemed really straightforward to me. The conclusion seemed simple, but the paper I struggled with a little bit. I don't know if anybody else read through the paper, but there's a lot of equations and um, uh, different perspectives on kind of the same stuff. Let me just take care of this real quick.
Yeah, you said you read it already, is that right?
Kelly? Yep. Okay. Did we have any other people that read it? Okay, Ted, great. Good,
Well,
good, good.
no.
Okay. Oh, Hitch, great. Glad. Hopefully you guys can help me out.
I'm good.
Okay, so let me just get started then. So what I'll do, like I often do, is I have slides with some kind of highlights. We'll go through that. We may jump back into the paper as well as we do. I'll also say again, standard rules for this group. Free to interrupt, ask questions. We'll keep going until we've got all the questions answered. We don't mind stretching it out to multiple meetings if necessary. So. We welcome the input when we think questions actually really add to the quality of the meeting. So let's see. So I've got to share screen. Everybody can see that, hopefully. Is that coming through?
Yeah.
Okay,
I don't see shit.
It came through on my end.
great.
I don't see shit.
Okay, so let's see. Okay, so this is the paper. I think it's all OpenAI authors as part of it. I wanted to start with kind of the standard. A lot of these we seem to have the transformer pictures, background or foundation to build upon. So this is from the Attention is All You Need paper, and it introduced the transformer architecture. The Most of the models nowadays only use the
Hey, I
right-hand
think Dave
stack.
has something to say.
All right, so this is the transformer architecture. The paper is actually based on analyzing transformer models. So this is a little bit important. The key thing being that, okay, most of the models these days now only deal with the decoder model, this stack on the side. And this paper separates the concept of these embedding components, which take the tokens and put them into the embedding space. I think they didn't say it explicitly, but I think they also exclude this linear projection layer at the top that projects back into the token space. And so when they talk about parameter space, they're talking only about the attention models and the feed-forward networks. And again, these are repeated n times for n layers. So just wanted to touch that real quick. Also, as kind of foundation, loss functions for language models. What is that? And basically what we're talking about is language models are trained by predicting next token in a sequence. And the loss is using cross entropy to measure kind of the probability of the next token in the test sequence based on the prediction of the model. I hope I got that right, Ted. I think I did. So this it gives the true next word high probability is if the loss is low and it's good. Cross entropy, for those that haven't covered it, and I'm not really great on this, but it measures basically the the difference between the predicted distribution and the actual distribution for next token. And down here, cross entropy, this is the equation for cross entropy. So for a given test set, it's the negative of the average, so the sum of 1 over n gives you the average of the log of the probability of that next token given the model prediction Q. And in the original equations, it was based in base 2. I think that's called the Shannon entropy. But the reason it's interesting here is in this paper they referenced NAT, which I went and looked up, and basically NAT is the same thing, but instead of using log base 2, they use natural log. So,
Hey,
okay.
Roger,
Yeah.
do you know why they switched? Is it a better metric, or, I'm just wondering.
I think it's just a different, I mean, it's just a scaled difference when you change the base on the log. I think that, you asked the question, well, why 2? Why was it 2 to start with? Why did Shannon use 2? He characterized things as kind of bits. Yeah, I don't have any better answer than that.
Maybe it's faster. Maybe, maybe your optimized log function isn't base 2.
I mean,
Although
just
it should be.
yeah.
Just the exponent, Yeah, I don't know. It's crazy. Yeah, but
I mean,
it could be that,
literally just a constant scaling.
Right.
It's the natural log of 2 is the constant that turns one into the other. You multiply or divide by that. So there really is no conceptual difference. It's, if you looked at the curves that are identical, it's just the labels on the y-axis. So, but yeah, I think like Julia said. So originally, if you're doing information on a communications channel, then bits is sort of a natural way to think about, like, what's the minimum number of bits you need to encode a certain set of information. But
Okay.
when you're doing more theoretical stuff, I'm guessing it's more convenient just to use natural logarithm.
Yeah. Okay, that makes sense then, Ted, now that you mentioned the background coming out of like communications type, thought process, if you will. Okay, thank you.
Sure. Okay, and so one of the things I read kind of characterized this is what was the objective of the paper, and really if they were trying to figure out, if we've got a fixed budget, compute budget, what's the best model size, and what data size do we need if we want to achieve a low loss. Now in this, almost all this discussion, they talk about the loss again as that cross entropy loss. And it doesn't talk about, okay, so what does if a better model is a lower loss model, it doesn't really project what does that mean in terms of downstream tasks. But we're just focused on getting models that achieve good prediction for next token. So it's the pre-training part, I guess you would say. Okay, and the paper, again, I'm doing this a little bit out of order because I had a hard time kind of assimilating the information, but this seemed like this was the core of the paper in a way. So in these 2 plots, we have horizontally on this one is the number of tokens processed versus vertically is the loss, and that's a negative log likelihood, I guess, on the left-hand side. And then the different color lines are different model sizes. So given a model, so take the 1,000 parameter, you process more and more tokens, eventually your loss starts coming down, and then it hits some sort of plateau here. Now I didn't hear them say this, but my intuition here is on that plateau is it's kind of like that model at that size is saturated. It's like that's all that it can hold. It's reached its capacity. And as you increase the model size, your capacity increases and you can predict better and better next tokens. So a really interesting thing here is this larger models require fewer samples to reach the same performance. So that's kind of cool. So like if I'm picking 8, for instance, if I have a small model, I need whatever it is, close to 10 to the 9th parameters. And it looks like if I have a large model, then it only takes probably a tenth of those parameters. So it's actually, this seemed counterintuitive to me. So if you have a small data set, you actually want a bigger model, which is kind of weird. That you'll get a better loss. Ted, am I saying that right? Do you think, or you?
So this is an instructive first step But what they haven't factored on the left side is how much more expensive the large model is than the small model.
Yeah, we'll get to that.
On the
Right.
right side, you'll see that actually if you have unlimited compute, you always want the largest model.
Well,
So
I mean, I think
But a
I'm
limited
thinking about
data
this
set.
a little bit in contrast with some of the other situations, right? Where you have memorization, you have models that tend towards memorization. You can have models that tend to learn less fast. I think this is also a side effect of the transformer large language model architecture, that it does have these curves, because not all models have these curves. I think that's the interesting observation, right? I mean, this is interesting, I think, and it's not necessarily, I think to Roger's point, it's not necessarily intuitive that the specific shapes of these curves with those many parameters occurs that way, because that's not always the case. Yeah, I mean, I'm assuming that this is all outside the space of memorization possibilities, though, that the data set has to still be larger than the number of parameters, essentially.
Yeah, they have regularized these models well. So that's a great point, Sally. So these don't memorize, they don't overfit.
Yeah, I think that on the left-hand side, I do think that they have, like you can go up to 10 to the 11th. So that I think that data set is very large. But I'm not sure to answer that question. So is it, Ted, at this point, I probably have, this is 10 to the 9th parameters, and this would be down in the 10 to the 8th data points.
Yeah, I think in this paper, you should always assume that every token is unique, that they're never repeating data.
Yeah.
So
Now,
it's a lot harder to overfit, right? In the old days, like you train a CNN, you might do many, many epochs on the same data. In this case, you never see the same sentence twice unless it actually literally happens to be out there twice, once in Wikipedia, once in Harry Potter, but you're never going to process literally the same source more than once.
Yeah.
The other way to put that would be that you do not finish, you do not have multiple epochs around the same data set. So potentially,
you don't have the memorization tendency in the training approach as well, is what you're saying, is that right?
Right. So now no chance to re-look at the same sequence.
So does anybody have any insight? I didn't kind of understand this first little shelf. Like, why are we out to 10 to the 8th before the model starts to improve at all?
I can answer that one. I've been thinking about this a lot. Well, at least I can try to answer that one. So we just made a reference back to CNNs. If you think about the original 50 seminal papers on CNNs, one of the things as we started developing the first big neural networks, like the first deep neural networks, right, was the initialization value. There hasn't been a paper about initialization value in like 6 years or 7 years, but that was entirely, if you recall, right, like that was entirely like a huge surface of research that was being done on the original neural networks, because if you did not initialize the values correctly, you would kind of shoot off in a direction and you could get lost in these local minima that were infinite spaces, and you'd never ever recover. And so my sense in looking at this is that as we're looking at these different curves, you're essentially building models that are robust to that, but they have to deal with the cold start problem, and that's essentially the shelf, is that you're getting yourself into a state where you're ready to absorb information and actually learn. That was my intuition immediately when I saw that.
Okay. So Ted had said at one point that I think you had presented it as kind of these large models. It's kind of like the lottery ticket hypothesis, where there's some, in the case of a large model, you may have some subnet that just happens to be initialized well and can learn quickly. So if I invert my question, I guess I can see that these large models then following the yellow line, it's like they're tuned, they can get started more quickly, whereas the other ones, Sally, you're saying you have to get out to
And,
this.
and that they don't need that they can do a little bit of memorization if you not quite memorization, but like they can generalize more quickly than a small model that has very constrained in terms of what it can move at the very beginning in terms of that concept of discrimination. A very large model can hold on to a lot of potential discriminators very early on and be wrong about 50% of them and still have signal. Whereas a smaller model has to be much more constrained in what its initial discriminators are.
Yep. Yep.
You
Okay.
know, sorry, if I could add, like, it was not clear to me how to answer your question. I think one of the things that this points to is that natural language is a hard problem. If this were easier, I don't know that, if it were MNIST, I don't know that the small models would start learning later. But because language is so freaking hard that basically where you see it at like 11, it's basically like doing no better than random guessing.
Yeah.
You know? So it takes a lot of work for it to just even break better than that.
Also, every mammal has a neocortex, but only humans can do language. So there's something tricky about it.
Right, and kind of to elaborate on what Ted is saying. So even though with ImageNet, with relatively low frequency images, when I say relatively, when we try to apply the same models to medical images, it takes extra effort to kind of, for each task, be able to figure out how it applies, depending on the image's characteristics. And that's where, I mean, to some extent, if you go a little more, double click on the images or vision domain, starts to get trickier even there, but still not the same level of complexity as language, where a picture can be described in so many different ways, but when you look at it, there are only limited number of ways you can interpret it, more or less.
I asked one of my smart friends this same question, and he didn't have a good answer. So just thought I'd share that.
Your smart friend needs to go back for some more training. So on a better data set.
I don't know if you saw that, but ChatGPT thought that the answer was that it would have a very steep learning curve initially learning some of the basic features. And I think that points to Ted's point, was that if it were an easier problem, you would have a quick set of learning on the early training. Whereas instead you have to get those early, you have to learn even those early features, because language is a hard problem where you're essentially first learning the features, then learning about the features.
Your smart friend reminds me, what was that movie where the guy was dating the AI and he was heartbroken when he found out that the AI had 5,000 other boyfriends as well?
It's called The Last 5 Years of My Life. Thanks a lot, though. Thank you, Roger.
ChatGPT's become my good buddy too. So, all right. So here, so that was one of the things. So that, as Ted mentioned, the interesting thing here is that so the large model learned it, which with a tenth of the tokens processed that the small language model, because there's so many tokens, or excuse me, because of the size of the model. If you look at it a different way, and here they use compute petaflop days versus loss, and again the same coloring on the model sizes. Here you can see that to learn, like say we're getting to level 8, to learn that more quickly would cost, what is that? Ooh, maybe 10,000 times more compute. So it's a lot more expensive compute-wise, even though you learn on fewer tokens processed. And the other interesting thing here is that you can see how these curves, when you plot them versus compute time versus tokens processed, you get into this geometry where this little curve where the models start to become saturated, in this must be kind of a log plot, is it? Log semi-log, but it's against negative log likelihood, so it's kind of a log. This line, these corners kind of form a little boundary here, a little line, and that's the important thing. And what they say is that, you know, if you're gonna compute to some level of loss, then you can do it with a small model, and, you know, train out for a long time after it's become saturated, or you could just train it with a bigger model, and it'll get there more quickly. So the optimal trade-off from a compute perspective then is to pick a model size where you're just starting to saturate along that boundary. And I never quite understood where they mean, do I cut it off here right at the corner, or do they go a little past the corner? I don't quite know which one of those. Does anybody have any insight there?
I found that hard to read too, but what I'll say is that's much simpler is on the left, you'll notice none of the lines ever cross.
Mhm.
So what you said is with no compute budget, you always want the bigger model. Okay. If lines cross, then that means that which model you want changes between the one side where they cross and the other side where they cross. And so this means that there is a time when you would actually want the bigger model instead of the smaller model for the same compute budget.
Oh, if it's, yeah. So there's a time when you'd want a smaller model.
Yeah, so if you look at the very smallest model, the far left purple line, right?
Yeah.
You get good performance the cheapest when it's going down. But once it starts to plateau and it crosses the line that's one to the right of it, then you actually would prefer to have the one that's a little bigger. And that's true for every one of these, is that there reaches a point where you want the one that's one bigger.
Right.
Well, I mean,
So
the
the other
bad
way to
thing
look
about
at
this,
that-
though, is it states that basically compute budget is not directly, because it's not linear, but like is deterministic of the quality of your model, at least according to this. Richer
Right.
people get richer.
Well, it looks like there's a hard floor if I'm looking at that on the loss diagram there. That, you know, you could train that first one forever and it's just not going to get any
Now
better.
get down to it. Yeah.
Yep.
Yeah.
So,
Yeah,
but
it just
basically means
can't
that you want to
afford-
make the largest possible model and have the largest compute budget possible, and then you have the best possible model.
Right.
So
But given a budget, if you start with a budget, this
Yes,
tells
then you can figure out
what-
which one's
yeah,
best.
There are some models that are too big, and then there's other models that are small, and there's one that's just right.
Right. So Roger, so basically the starting point is how much compute budget you have, and based on that, and potentially also the amount of tokens, number of tokens that you have, but the tokens don't really play as much of a role as the compute budget, and that decides your. So the second graph decides which model you want to go with, and then you have to process those many tokens to get the right. Now the other thing is, of course, you know, the curveball could be that, well, midway you got more resources, then you have to start over again. But then I think our friend from Grok or Microsoft, the MUP, which is new hyperparameter, can be leveraged at that point in time. But I'm you know, that's just a curveball I'm throwing there. But long story short, you start with the compute budget and decide your model.
Yeah,
but if you
and
get
that's
more,
what they set out to. Yep.
Yeah, and
I
if you
mean,
get more
it's a little
budget, then you have more techniques up your alley to use.
Right. And this is where to me, it feels like this set the trajectory for OpenAI. That we want to get better. We need more compute. If we do more compute, we're going to get better. We know it. We can show it. Give us the money. We'll get a better, lower loss.
I mean, could the interpretation of the one on the right be like if it's got more parameters, it kind of takes longer to converge because it's like you've got a lot more parameters that you kind of have to kind of get on the same page, so to speak.
Alan, that would have been my kind of intuition, is if you got a bigger model, obviously you're going to need a lot more tokens for it to start to the model, the parameters to get adjusted so that you get good prediction. But that, I think the diagram, if I'm reading it correctly, on the left actually says the opposite. That is, if you have a big model, given the same number of tokens processed, the big model will actually do better than the small model. So it's kind of backwards from what I was thinking. I always thought bigger model, more, you needed more tokens to tune it, but it's really if you're doing it at a ISO loss level, then it's the bigger model tunes more quickly.
But aren't there two regimes? There's the overfitting regime and then the generalization regime. I don't know if that's the right words. But, in other words, the big model can start out just sort of memorizing things like crazy, and then it's forced to generalize later in its training. So that
Are you talking about the double descent, Julius, or are you talking about the general bias variance? What is that thing called where you overfit
bias variant trade-off?
Yeah.
Yeah, I think it would be both. So in these curves, the initial descent would be, more memorization, right? And then the later stages in the plateau and so on, that's where it has to generalize. So it's just a hypothesis that that's where the faster descent comes from for the larger model, because
Julius, to Ted's earlier comment, though, I think the assumption here is that you will always have enough data that you're not going to be able to memorize.
Right.
And why does it do any better at all? In other words, so the job is prediction, and nobody's seen anything twice. So why would the larger model do any better at all? Because all the models are flailing around.
So it has, what I'm guessing is that it has the capacity to know that we're telling a fairy tale story about a prince and a dragon. And so I know I can predict a princess is going to be a token that's coming up soon. Whereas the smaller model doesn't have the capacity to make that prediction. Even though it's the first time it's heard this particular story, it's seen the pattern.
Yeah, that's
my
right.
Intuition.
So a very small contribution to why big models do better comes from the fact that they're bigger and they actually understand grammar and vocabulary and blah, blah, blah better. Only a tiny amount comes from that. Where big models beat small models is not early in a sentence, it's late in a passage. So if you said, I'm just going to have the two models predict the end of the first sentence of each Wikipedia article, you probably don't see that much difference in the performance between GPT-2 and GPT-4. But if you have them predict the last paragraph of an entire Wikipedia article, that's where GPT-4 is going to smoke GPT-2.
So Ted, have you implicitly introduced the hyperparameters like the context length and a gradient accumulation or whatever could there be?
Well, okay, yeah. So that's a little bit cheating because GPT-4 actually has other advantages. But I'm saying if you trained two models, one bigger that were otherwise, the same context length, the same other kinds of things. We'll see. There is a chart, a figure in this paper where it shows something, and you see that the small models eventually plateau, and the bigger model keeps getting a little bit better as you get later and later tokens, and that's where they actually really do their winning, is the later tokens. Does that make sense?
Julius, that sounds like another one of the experiment for the VSLM project, because understanding, so Ted, you were talking about this, the further out you get in the sequence, the better the prediction. Like when you get into context learning, the slope of the line is supposed to go like this. So what you're telling me is that that's not only learning in context learning, but it's also model size. That larger models should be able to do that longer into the sequence before it plateaus.
Yeah, it turns out it's not really a line, it's a curve. And the beginning part of the curve looks the same for many size models, but for small ones, it'll peter out and flatten. And for larger ones, it'll go longer before it peters out, sort of. And again, we'll just see it in the later figure in this paper. You don't have to take my word for it.
One question I had. Go ahead.
Well, hang on. Shulin, you had your hand up too. I noticed
sorry.
there.
Yeah, I was thinking about another explanation that will work is that when we have more parameters, it might be easier for us to find the to achieve kind of like a minimum. Yeah, but I was thinking that like because like usually when we are training the models, we're using gradient descent. So yeah, but I haven't finished my logic, so I need to check out. Yeah, I was thinking that like because when we have more parameters and we are using the same kind of like speed of doing gradient descent, it might be easier for us to achieve the local minimum with more parameters. Yeah, but I think I need to read more through the mathematical proofs.
Shalane, I think that's similar to what we were saying about Ted's comment at one point where larger models may have a bunch of sub-models that just the lottery ticket hypothesis where sometimes you just get good initialization. That's similar to what you're talking about is you may just have, it's not a local minimum, but it's a, because local minimum implies you're kind of trapped. These aren't local minimum, these are good minimum.
I know. Okay.
Yeah.
What?
Yeah.
Mixture of good guesses.
Yeah, exactly. New model.
I
One
think
thing
there's
I
a
did-
paper named that.
One thing I was wondering if anybody has insight. So in the small model, I see it come down curve and then it gets pretty flat. The yellow one doesn't really flatten out. It seems like it has a slope still. And I don't know if that's real or if that's just kind of we're on the curvy part of this and we haven't gotten to the flat yet.
So
Did we lose Ted?
yeah, so I'm still trying to reconcile these two graphs. So is the compute is the amount of compute per token, is that constant across parameter sizes, or is it the more the parameters, the more compute?
You're talking
You
about
need
this
to-
plot over here?
Yeah. The more is it
Yeah,
it the case the more parameters you have, the more compute to process a given number of tokens?
Yeah, it takes, right.
Is
So
that
up here, the compute is equal to, they use the term 6. I heard when it's distributed, that number constant's actually 8 times the number of parameters times the batch size times the number of steps, I think they call it, right? The mini batch counts, basically. So if you have a bigger model, then yeah, it takes more compute to get the same number of steps. And over on here, we're just talking about all these guys would have had the same batch size. And so that the number of steps is equivalent based on the number of tokens processed, basically. So yeah, Julius.
Yeah, so my question is, these curves are just really suspiciously parallel to me for a gradient descent in an optimization of a nonlinear system with random tokens coming in. I mean, is this cherry picked at all, or is it really like this? Is this really the way it always is? I mean, those of you with real experience should know that, this doesn't always happen, right? I mean, don't you
Somehow Julius ended up in the waiting room. We don't ask questions like that here. Everything is consistent and is the same, Julius.
This is an academic point of view.
Aren't you from the publisher parish scheme, sir?
Yeah. Okay, well, so yeah, you always do pick your best figures.
Yeah, I was going to suggest that, but
But it's it's really true.
Julius, is I think all these lines, all these data points were trained on the same data set. And so it's the same distribution, whatever. And so you're going to see this. If you actually did much more like random text off the internet, then you might get some lucky and some unlucky text. But in this case, they trained it on the exact same data set. So you're going to see much more consistent performance.
And would they use the same model initializations to the maximum extent? In other words, the first, 10 to the 6 weights are identical, and then you just come up with new random weights for the larger models. In other words, it looks like there's a lot of normalization of, the random numbers even.
Yeah, it's not today's recipe, but it's the same weight initializations in various places, you know, and whatever, and then same 10% dropout and same data and same whatever. And I don't know also if any one given data point. So like, you know, what loss did you get for training a 10 to the 3 sized model on 10 to the 6 tokens? That could also itself be an average of 5 runs. And that would smooth out the lines too. I don't remember the details and I didn't reread the paper that closely.
Okay, thanks.
Okay, anything more we want to extract from this? This again was, it seemed like it simplified it for me the best.
So actually, when they do this, when they do the experiment, they add more parameters. So do they add kind of like the diameter, the dimension of model, or they add more layers of the model?
So that's one of the things that we'll see, I think, later on here. They basically said that this scaling, it's strongly correlated with the scaling factors, the number of parameters, the amount of data, and the amount of compute. But it's very weakly correlated with model parameters, model hyperparameters. So the size of the model dimension, the number of layers, that didn't seem to have as much of an effect. When you got really at the extremes, like between 1 layer and 2 layer was big, there was a big change. But for the most part, as long as you're within a reasonable scope, the model didn't seem to have a big impact. Now, what I would say is, from what I read, it sounded like they only really played with transformers. They played with the width and the depth, how many layers and how wide is the model dimension. And from those parameters, they concluded that the model didn't have a big impact. They didn't explore other things, like in our VSLM discussions, we talked about, you know, having different changes to the topology. So maybe not all the layers are the same model dimension or that type of thing. They didn't play with that. They only played with change the size of the rectangle, kind of, if that makes sense.
Thank you, Roger.
Mm-hmm.
Yeah, and if you fast forward a few years, we have learned since then, there are architectural changes that make some slight changes. Data quality matters. You know, Mixtral is using a mixture of experts, and so then it changes the curve slightly, whatever. So it's not that nothing matters, but as we'll see in the other charts, that whether you do like whatever 10 layers and 15 wide, or you do 15 layers and 10 wide, if it's the same total number of parameters, it made very small, like 2% difference in your final result, something like that.
And it would be really an interesting experiment to see how many layers you can go down before it does start to go up, because that would be an indication of how much actual hierarchy there is in the model. You know, you can imagine that if it's fundamentally a 6-layer problem, then anything over 6 will be about the same. It's just the total number of parameters. But when you get below 6, then you start getting that inefficiency of, like, the difference between a 2-layer universal approximation and a 1-layer universal approximation, which is just vastly different. You see that?
They didn't, yeah, they didn't really. So this was the only one I saw where they talked about it, and they showed this little blip in. So this is compute versus loss, and they talked about a little blip in here. That blip, I think, was related to 10 to the minus 5, the blip from 1 layer to 2-layer networks. But that was the only one they talked. I'm surprised they were even playing with 1-layer networks, actually. But I'm also, I don't think they provided a lot of detail. Maybe I missed it in some of the appendix. They didn't provide a lot of detail on the way they played with the dimensions, the architecture. Yeah, I didn't see that. So, okay, moving on then. That's that one. So this is then kind of the results are they identify this loss of optimal compute, where if you given a compute budget, you want to get down to a particular loss size so given a budget, I can tell you what loss you're going to get down to. And I can also tell you what model size you're going to want to use to get down to that budget. So these blue lines are the training trajectories at different model sizes coming in, and they're kissing this little line here of optimal compute. So that you can choose that then. Amount of data is going to flow from that. You need a certain data size so you don't overfit. But you know what, given a compute, you know what loss you will achieve and what model you need to do it most effectively. That was kind of the goal. Okay, so then it's also data size given. So if you're doing all the other stuff right, you got enough compute, you got a big enough model. What they're saying is based on the data size, I can tell you what loss you're going to get down to. So here's one kind of hidden caveat in this, and that is that this is all based on WebText 2. So when they vary the data size, they're just subsampling the same data set. It's not talking about adding more data from a different size.
That's right. So the Microsoft Phi models were designed to be an experiment to say, if you had higher quality data, is this power law,
Yeah.
slope of it, are the constants different?
Yeah, so you would probably have, well, maybe even a different slope, but you're going to have a slope probably, the more is better. And it may be offset up or down, I would think, from that. But yeah, this conclusion seems a little, it makes the assumption that WebText 2 is the only thing you can sample from.
Yeah, I don't think they were trying to imply that nothing could change it. They were just saying this is a generic quality internet scrape kind of a data set.
Yeah, yeah.
Well,
Yeah, I guess
someone, yeah, I heard someone say that that's kind of why like the llama models are performing better and better because of the data quality. Was it someone here who said that, or did I hear that from someone else, or did I mishear that?
I think Ted's comment was it's the Microsoft Phi models are the ones where they really started, they analyzed it from the perspective of data set quality. The paper referenced later, it's textbooks are all you need. It's smaller, higher quality data set.
Yeah. Hey, Roger. So just to, I think Alan's question.
Yeah.
So that is true, and that is what the point that you made is observed in many communities as well, and that is why what they are finding out is that quantization of Llama 3 models in particular is not giving those drastic improvements as they used to have in the past, because apparently, they may be leveraging all the dimensions and all the bits as much deep as needed with the more number of tokens that they're processing. I don't know if that answers your question, but that's the generic trend with Llama models that they're seeing.
Okay.
What was that, Dave? Did you say that the Llama models are not?
So there is, no, they have improved a lot. So typically quantization helps because that means there is redundancy in the models, right? So you can quantize and do well with a smaller model by quantization, using the quantization technique. But with Llama 3, because the number of tokens that have been used to train it has doubled or tripled since Llama 1 and 2, or maybe even more. And the weights have learned a lot more characteristics of the language model as compared to the previous Llama versions. So when you quantize, you are not able to retain the same level of.
Okay. Okay.
Right. You follow what I'm saying, right?
Yeah. No, I think so. You're using more of the bits in the full model, so you can't benefit from quantization as well.
Yes, and I think that's what Alan was trying to comment, if I'm not mistaken.
Yeah.
I was more to, I was more saying that I heard that's what like the more recent Llama models did, but I thought someone might have said that here, but it might have been somewhere else.
Yeah, I think you're right, Alan. And to a certain extent, these different models, they all vary. If you look at the the details when they say, what did we train it on? You'll see something like, oh, Wikipedia, they used like a much higher sampling ratio than they used for just like the big giant web crawl text. And that helps improve their quality. But then you're right, like extra things they do to eliminate duplication and other things like that. So there's like literal repeating stuff, but you know how I was saying, like there could be a line from Harry Potter book that appears both in the Wikipedia article about Harry Potter and the book itself. And it could appear in articles about Harry Potter. So like you could get that kind of redundancy even without repeating any one given source. And so if you're the meta folks that do Llama and you work on cleaning your data like that, then you can improve your data quality too.
Dave, you had a question? Oh, no, hands back down.
Just a comment that to elaborate on what Ted was saying. So in the last year or so, there has been a lot of effort in finding the high quality data. So those curves that you see with the data sets, they are highly dependent on the quality of data. Just recently, I think it was a month or two ago, Databricks had a paper where they have internally, but not released, C4 large and small. C4 is that colossal corpus something, I don't know, internet data. And they have done some special tuning or curating of the data, and they have like a smaller and a larger data set, C4 curated small and C4 curated large, and they see way better performance than for the same size model than the previously available models. So for every other, or not every other, for most other parameters being the same. So data set quality, there is a lot of effort going on, and of course, with the synthetic data and whatnot in the recent past, which I don't understand all very well as of now, but definitely data quality has a big role to play.
Okay, so this was the result then. This was curve fitting basically to those lines. So the scaling laws are basically, if we know, so here we have, if we have a certain number of parameters and we have enough data and we're, as much compute as we want, then the loss that we will get can be determined by this equation where you plug in your parameters using NC, which is a constant they have, and this power number. So again, it's just empirically curve fitting to the data, I believe. We can tell you what loss you will achieve when you train that to convergence. So the power, you see this as power scaling laws. It just relates to the fact that this is a n to the nth power. So that's where the power comes from. Likewise, if you have a limited amount of data, then we can tell you what loss you will achieve on that data. Again, this is with the web text 2 data set. Again, here they provide the two constants for that. And they also tell you how much compute it's going to take. So let's see, if you got a limited amount of compute, we'll tell you what loss you can get down to. This assumes that you're going to pick the ideal model size and that you have the right amount of data for that as well. So this is, given these curves, which we extrapolate, I think they said it was like, the compute was like, I don't know, 6 or 8 orders of magnitude, something like that. They sampled that. Data size, I think, was only a couple orders of magnitude. And what was the other one? Anyhow, of these dimensions, they did a lot of sampling to create that trajectory that we saw like this. And those then gave them these equations. So now we can really predict what the future is. If we're going to invest this much time, this is the loss we'll get to. This was an interesting thing that came up later, that these constants are dependent on the vocabulary that you use. I think these guys used a 50,000 token vocabulary, but the numbers that they're using are specific to that vocabulary. They're not, absolute numbers is what they captured. Yeah, Dave.
What's this thing about the batch size? Is it something related to what Shumin was trying to
Yeah, so
refer to earlier?
I dove into it later because I was confused about the batch size. They spent quite a bit of time talking about the batch size, and I didn't quite understand why, but that really came from another paper they referenced, which was MK4 or something like that, I think. So critical batch size comes from this paper. And what they're basically saying, if I understood it, they talked about the intuitive picture of batch size. So you can either have a small batch size, which will tend to have higher variance, and do a bunch of those when you're doing your gradient descent. Or you can do larger batch sizes, which will have lower variance and do fewer steps. And if you look at kind of the cost to do the compute versus the variance, what you find is that having bigger and bigger batch sizes is better until you get to a certain plateau, and then having bigger batch size doesn't really improve from a compute perspective your trajectory towards whatever your minimum is going to be. So there's kind of an optimum batch size where if you can do it this size, you'll get there faster because you're going to do fewer steps. It is important when you're able to scale horizontally, because you'll scale, if you're scaling based on distributed data model, you have a whole bunch of nodes that are computing the gradients, and then those will be aggregated somewhere. It's that aggregation is where if you have a large batch, you have lots of data aggregated and you decrease the noise of that batch. But at some point it's too big of a batch, and the value you gain on the noise, reducing the noise, doesn't work out to your advantage anymore. If you have a lower noise on your batch, you can take a bigger step, and that's why it allows you to kind of get there in fewer steps, and that's good if you're doing parallel. So that's the two extremes, and the critical batch size was that one right on the edge. Does that make sense?
Yes, thanks. Yeah. And by the way, even if you have if your batch does not fit, you can have aggregation techniques. So I guess at the end of the day, you can always accommodate whatever batch size is optimal for that architecture.
I've heard of that. So you do kind of micro batches where you'll do a mini batch, but you won't actually do an optimization step. You're just accumulating gradient more and more and more. And that seems like it does have an advantage because you don't have to do the apply the gradient update. But I think the main point they were talking about in this paper was not that you're accumulating on the same machine a bunch of micro batches, but more that you're accumulating them on a large number, a cluster of machines that are all collecting these gradients.
So obviously you get wall clock time improvement if you do it on multiple machines. But
right.
If I could say what you said in like really simple terms, okay, if you're below the critical batch size and you say, I'm either going to use batch size 32 or 64, okay, what they're saying is that with batch size 32, it'll be half the compute of batch size 64. But it will take you more than double the number of steps. So you will lose in the long run. You are better off going to 64 because you will do fewer. Each step will cost you twice as much, but you will do less than half as many steps.
That's okay. Below the critical size.
Below. Once you go past that, then one possibility is if you go way past it, okay, use a batch size of 1,000 versus batch size of 2,000, you will take 5% fewer steps, but each step will cost you twice as much. Why would you want to do that? Right. So that's why to them critical batch size is important. And since you're a company like OpenAI that has a lot, then you can actually reduce the wall clock by parallelizing. But even if you didn't, you or I, if we're doing a small experiment, we can do the aggregation, and it'll still reduce the total compute we need to get there. Mm-hmm. So it's not just a very abstract concept. It's like, yeah, you get real savings by increasing your batch size. And then you get to the point, that critical batch size, then you get to the point of diminishing returns, where you double the batch size and it no longer cuts your steps in less than half.
Yeah. And I think in this paper, there was some a formula for determining what is that batch size, what's kind of that optimal batch size.
I haven't closely read it, but they talked about the general noise scale of your data.
Yeah.
So,
yeah. So I hadn't thought about that. So even if I have just, 1 or 2 GPUs and I'm doing this, I actually computationally would be better off doing some micro batches where I'm not optimizing, I'm just accumulating gradient, and then every once in a while do the optimization. And that's compute better than just a standard mini batch.
Yeah, and in the extreme, you could just do batch size 1, just do pure SGD.
Yeah.
And it's going to take a gazillion number of steps.
Yeah. Interesting. Okay.
And is gazillion 10 to the what? Sorry.
Okay, so
one quick question. So the batch size, intuitively, I always thought of it as a kind of dither or a kind of a noise source for the gradient, because there is no, stochastic. As far as I know, atom optimization is deterministic and doesn't have, what we would call annealing temperature type stuff. So I always thought that was the temperature in the gradient descent of neural nets. But it sounds like it's not necessarily that, because you need that to avoid getting stuck. But in this case, you're not going to get stuck. You'll just take longer. So it seems like maybe that's not the right intuition. So is it just the optimal amount of averaging of various gradients, or is there some notion of temperature there?
I'm not sure the right answer. That paper, so I do remember there was a reference to a noise scaling in here. So this was the paper that he referenced, and they did talk about it somewhere, linking it into a noise. So yeah, because I also, Julius, I always kind of struggled with, I thought it seemed like larger batches would be less noisy, that'd be good, but I'd also heard a similar type of thing that small batches, you want the noise to keep you from getting stuck. And maybe this is just an attribute of these large models or something, I don't know. But it might be.
Here's a hypothesis that we could test in our, copious experiments. If it really is, essentially providing a temperature for, like simulated annealing, where, it's just dithering the gradient enough so that it can kind of get where it needs to go, then that would predict that there's a different batch size that's optimal as a function of where you are in the loss function. So you would have a fairly large batch size setting out, and then as you get toward the convergence, then you can shrink it down, because you sort of committed to where you're going to descend. And I don't know, just like, what do they call it? The learning rate curve. They have scheduled learning rates where they, start out with a large learning rate, and then you shrink it toward the end. It could be a similar sort of thing. It may be that there's you're not supposed to say this, a more optimal batch size schedule. Maybe we should be scheduling our batch size. Anyway, I'm just.
I think they do. No. I think
they do
that. I think
really?
they do that. Yeah, I think as you go along, because in there, one of these things they talk about the batch size. Well, I'll take that back. They talk about different batch sizes, but I had the impression they were talking about batch sizes that change as the noise level changes. So it's, if you're running at the optimal batch size, I think the optimal batch size changes over time.
Okay, cool.
Yeah, they were saying that bcrit changes as you train and as your loss goes down. So technically speaking, you could keep changing your batch size to chase bcrit.
Mm-hmm. Oh, I'm gonna have to.
But once again, Julius, going back to the beginning of your question, this is where LLMs really break the rules of everything we learned about ML and deep learning, because you can't really overfit if you're never going to see the same sentence twice.
Mm-hmm.
So it really is like, I'm just wrapping my head around. It's really like a fundamentally different problem.
What you're saying is you can't overfit if you never see the same sentence twice.
You can't overfit if you no.
Sorry. That felt like a demanded joke. There was no way around that. Sorry, Ted.
Okay, so those.
Let me repeat my words. Oh wait.
Let's see, this was just a quick summary of the equation. The predicted loss given the number of parameters and the data size can be determined by this. These are the constants that they empirically fit. And they did mention the equation 4.4 or something like that, that to avoid overfitting, you always need to have that number. So, whoops. That seems, I don't know, I guess that's a lot of data for small models, but it, I guess as this 0.74 kicks in, the larger models, yeah, I don't know what that equation looks like, plots actually versus n. But they are sensitive to that. We already visited that one. Notation, I think we already, so the loss, the number of model parameters n, the compute budget c, data size d, critical we already talked about. C min is, this is like, what's the minimum compute it takes to get to a particular loss level? What's the minimum number of steps that it requires, training steps required? And then the power laws, which we already saw. Summary of them, I'm not going to go, this is where it started. The first ones had kind of nice, simple, and I think you extract most of it. They looked at it from different perspectives here. Unless somebody Reddit's interested in diving down into those, I'm going to kind of skip through these, I think.
So that number that you had for number of tokens, that was what, 60 trillion or something? Is that what it was? In that where you said it?
Oh, the constant, you mean? Yeah, I don't know what number.
Oh, the DC is the constant, okay.
Yeah, that's just a scaling constant. I don't know how we should interpret that. What does that mean? What does the scaling constant mean? But I'm not sure.
It's just a constant. I mean,
yeah.
It doesn't really mean
and I think
anything.
they also said that there's
fitted.
a contradiction in their model if they predict it forward too far. You know that the entropy of the language has to be greater than 0 or something like that, and so there is a limit to where these equations won't carry on all the way. There's 2 lines of crossover, so.
Hey Roger, can I ask kind of a meta question? Sorry, just like putting together those constants and the relationships that we see between training, batch size, data set size, and compute budget. If we look at that as an optimization problem, like an optimization surface or performance surface, right? And then we look at it from an optimization problem perspective, it's clear what I do if I'm OpenAI, which is I get more money, I get more compute, and then I keep working on this problem.
Yep.
What isn't clear to me is what do I do if I'm not OpenAI? Well, like if I'm a professor at a university with a very limited budget, let's say like a second tier university like Stanford or something like that, right? And I don't have really everything I need.
Are you Berkeley? You must be a Berkeley guy, right?
I live in the East Bay, and I've converted. I'm actually, I don't even know if I'm a Stanford kid. I was just joking. It was just a jab at you. But like, what would I do, right? Like, how would I interpret this performance surface to be anything other than advantageous to the people that, like, you have a number of things that go to infinity, and OpenAI is looking at $100 billion valuation, right? Like your valuation and your amount of capital raised is starting to approach infinity at a certain point here.
Right.
Like, what do you do for anybody else? Like,
Well, so my kind of gut response to that is that I feel like these curves drove them down that particular business strategy. But what I think would be kind of interesting, and I'm hoping with the VSLM project we can do, is what they did is they said, identify these curves, and once you identify these curves, you can actually extrapolate it a long, long ways. So if I can find things that are improving these curves in the small dimensions of small scale, then, can I show that they then work at large scale and provide me big gain at large scale? So I may be able to make contribution, depends on if you want contribution or market value or capitalization, but I may be able to make contributions just by playing around on the low end of this scale with dimensions that they haven't, like data quality, like changing the architecture in ways that they weren't changing it. They only changed number of layers, and I think it was like the dimension, number of heads and stuff like that. And dimensions of the MLP. But they didn't play beyond that. I think they just started replicating the same thing over and over.
There would be opportunities for academic and intellectual contribution, but in a world where all the value curves pointed to infinity, even if I make an optimization, the party that economically benefits from that will be the party that can get the closest to infinity anyway on that new curve, right?
Yep.
Are there any pockets in here where you're like, oh, here's kind of an area of small models that are by themselves valuable, or like?
Well, I think
absolutely. All the little elbows on the right figure are points like that. So, if you have a problem and you can solve it with a certain amount of compute and quality, then you pick that elbow and you're at that size. So it's all about right sizing everything and minimizing cost per value.
So if we look at the chinchilla paper, they approach it different. They had, I think it's same kind of analysis, but they ended up with different equations that they fit. And they concluded that you needed smaller models, more data to train. But one of the things that they pointed out was a smaller model has an advantage. Even if you spend more compute generating a smaller model, it has an advantage in the inference phase from a cost perspective. So the niches that you can find is, there is a cost to run, a 1 trillion parameter model. If I can achieve the same thing with, a few billion parameters at a much lower cost, then I have a competitive advantage in that little sub-market.
Got it. Okay.
Yeah, and I think this is maybe easy to say but hard to do. But you can try come up with ideas that aren't LLMs that are kind of much more efficient. And I know it sounds easy to say.
Sacrilegious, push them out.
Yeah, but it could be something that, as I say, it's easy to say, hard to do, but it could be something that works better in certain situations, but not as generalist as, say, an LLM. And because I guess what you also have is that it's like that pressure to do that kind of forces you into that direction. Whereas if you do, then on the other hand, like if you're like OpenAI, it could be that all the resources kind of make you kind of complacent, that you have Microsoft in their budget, and there's not that pressure to really come up with breakthroughs that don't require that much compute. I think there's again, I say easy to say, harder to do, but I think you can kind of take comfort in that.
And they are doing that. They have people at OpenAI who are downsizing. ChatGPT 4.0 is much smaller now than when it first rolled out, right? So you come out with a new frontier model, and then it gets smaller and smaller, and they try to not break it, but they do. It gets worse. You can tell. And
I
then,
didn't know that.
Oh, I really noticed it.
No, I didn't know. So they distilled down the model?
Yeah, they're constantly reducing its size. And then the new frontier model comes out, and it's just like a giant breakthrough, and then they downsize that. And I've seen a figure. I'm going to see if I can find it right now.
Yeah, that's interesting. That's good. That's good.
I thought that was partly for financial reasons as well. It's that it gets them a little closer, not quite, but a little closer to profitability if they can downsize the models.
The other thing I would add is that it talks also to deploying on smaller and smaller platforms.
Right.
Right.
And especially, this thing, the phone, right? Billions of these, trillions sold, whatever. If you can get something that runs a little bit better on billions of platforms in a lot of people's hands, financially, that's a win.
Yep.
And they're losing money on inference right now, right? I mean, these frontier
Yeah.
models that we have access for $20 a month, I don't think they're making a profit yet, right? So they have to distill them down
No.
before they can even turn a profit. I think Claude and OpenAI and maybe even Google are losing money on inference with their, public facing models. That's just a guess. I don't know. But I bet it'd be at the beginning, they definitely were.
Well, I think, you have to look at how those big companies run those models. We're talking about a lot of detail and things like that. But a lot of people just want to use the model and will pay money to use corporations, that sort of thing. So if you view it as a service, there's a different economics, I think, to it.
Okay.
It's about GPT-5.
I cut off somebody.
No, that was me accidentally starting a video. I was trying to find the
Oh,
stick.
Okay.
So
Yeah.
I saw on a YouTube.
contrary to our norm, I can't continue next week. So I'm going to try to, I'd like to finish up tonight and I'll try to speed it up so that we can get there. But yeah, so, okay. So this was one graph that I thought was kind of interesting where they talked about, yeah, okay, but what if I'm not at the optimal, that compute, optimal compute point or boundary. And they talk about, yeah, if you have a model that's half to twice the size, it'll cost you a 20% larger compute budget. So you might, maybe you misguessed what size you wanted or something, or maybe you can't afford, you don't have enough compute, big enough GPUs or whatever to load a particular model size. You can run with a smaller model. It'll still work. It's just it'll take 20% more compute budget to get there. It'll take you a little longer, and also it'll not only take you longer. It takes you longer to get there with the smaller model. So that was interesting that they looked at it from that perspective. This is where they played with the feed forward ratio. So the dimensions of feed forward versus the dimension of the model. And I don't know the feed forward. Where's the feed forward parameter in there? Feed forward ratio. Okay, so that's like 10. So that means that I assume that that's that middle layer in the MLP, and the feed forward is 10 times bigger. This, when it gets really small, that'd be kind of weird. I'm not sure what all that's adding at that point. I guess it just adds fewer dimensions, doesn't it? If it's usually they fan out to a big internal dimension, then bring it back down to the model dimension.
Yeah, so Vaswani, it was 4 times, and lately we've seen people use closer to 3.5.
Oh, interesting. Okay. Wonder if that's driven by this at all. Aspect ratio. So this is kind of like I was thinking of as the rectangle. How wide is it? How deep is it? Type of thing. And attention heads, not too surprised that doesn't make much difference over a factor of 10. Anyhow, all of them, it didn't have a big impact on the performance. I guess in this middle range where we typically see is down near the low point, the optimal. They did say that diagram that I showed in the beginning, these numbers all work better when you use just the model dimensions. You exclude the embedding and the projection head. So this is different ones. If you include the embedding, this is a nice straight line. They all line up. When you exclude in the N, you exclude the embedding and projection heads. This is one that we've talked quite a bit about data set quality. And I thought maybe they'd address that, but then I realized that no, these are still trained on the web text too. And then they say, okay, well, how well does it generalize on these other ones? They didn't compare like learning speeds on the other data sets. They always trained on web text too. So it didn't give the information that I wanted to see, but they did show that, you know, regardless of the number of parameters or somewhat independent number of parameters, you generalize about the same from the web text 2. Okay, we already went through critical batch size. Okay, so this is where I kind of captured things that I was thinking in terms of nice paper, but what was kind of left out or what could you miss between the lines? And again, it's the data set. We've talked about that. How does that change? Phi was the one that I forget who it was, Ted or Dave mentioned that was one where they really focused on data set quality. In this case, they did look at LSTMs, but you know, I mean that's not the fact that LSTM architecture didn't improve it doesn't mean that there aren't other architectures besides transformer or tweaks on transformers that can't be better. But they mostly played with parameters that didn't change the overall architecture a lot. I like this idea that it's a very simple to measure, that the log loss is a very simple parameter to measure and see the improvement. So that's cool, but I don't know how that impacts downstream tasks. If you're doing question and answer or whatever you might be doing downstream, does it mean if I double, you know, or cut my log loss by, you know, a factor of 2 or something like that, am I now that much better at telling stories or answering questions or summarizing papers? That I don't know. I don't know if anybody got insights on that. So that seemed like a hole to me.
Yeah, that's very tricky. And that's not only task and also data set dependent. So for math and reasoning and, you know, depends on the data set and on the task, and it varies a lot. That's why you oftentimes see these LLMs publish numbers for different data sets because, you know, so I think you're talking about two things. One is the trend. The other is the overall performance impact with the pre-trained model. But I wouldn't be able. I mean, I think it depends on data set and also the task.
Yeah, and that's, you know, when you were starting at OpenAI right at the beginning and you said, hey, look at this trajectory. If we get 100 times more funding, we can get a bigger model and we'll be this many gnats better than our current model. Did anybody say, okay, well, what does that enable then? What does that mean that model will be able to do that I can't currently do? I didn't see anything about that in here, and I don't know if anybody else has heard. The other one was the chinchilla. So Julius, you had mentioned this as, hey, wasn't this the follow-on? And this is from, I thought it was just the next paper from the same group, but this is from Google, DeepMind Group. And they basically did similar types of analysis, reached the same conclusion. Why else does that British? That must be, because that's London, DeepMind's in London. Okay, so here they're saying that, yeah, increase of 10, for example, if you increase the budget by 10, they suggest you should increase the data by, I don't know what that is, 5.5, while the data size, the training tokens increase. Okay, this is the model size. The model size should increase by a factor of 5, but the data is only increased by 1.8. These guys went the other way. They said you want to increase them together. So they had similar equation. This is their law, which is similar to the OpenAI law. But they ended up with different coefficients for these guys. And so this was the plot that they have where they were saying the scaling law paper drove people around making really big models and don't train them on as much, you don't need as much data to train them. The chinchilla came out with this chinchilla down here, which was a deviation from that, where they said, no. Let's instead train it on a smaller model with train on more data. And it plots on a different line where we're doing computation versus the number of parameters. So a smaller model, but same number of flops for training. And that has downstream benefits because inference is better, et cetera, et cetera. Inference is cheaper, rather, I should say, et cetera, et cetera.
You have a hand raised, Roger.
Oh, sorry. Yeah, Nav, go ahead.
Oh, yeah. So just wanted to add on the previous point that for the downstream performance, I think Llama 3.1 already went ahead and did the next step where they produced all this scaling laws based on the downstream task, which is kind of crazy, which is, as I would think of that as implicit overfitting to the downstream task. But instead of just focusing on the next token loss prediction, they just took a bunch of tasks, whatever open benchmarks they cared about, and then produced all these laws, and then try to conclude what's the right, model size, etc. would they require, and that's how they even came up with the 4 or 5 billion parameter. So basically, as big as required to beat or get good enough performance on the open benchmarks.
So what is that paper then?
This is a Llama 3.1 paper. I can say the section 3.2.1.
And that's where they derive their own laws based on downstream tasks.
Not the own laws. There's the scaling laws. So scaling laws basically the same that everybody knows that it holds true for the next token loss prediction. But a flaw there is that, well, what does it mean even predicting the next token, right? Is it really reflective of any real intelligence, etc.?
Yeah.
So then they went ahead and then they said, okay, fine, this is a little bit noisy and there are some flaws in that anyways. So let's just start to plot the laws or plot the losses on downstream tasks. So basically you take like all different variations of permutations of model size or Llama 3.1 size, dataset size, even dataset mixing, dataset sources, and then you just plot all these curves, and then you finally come up with the recipe and model size and everything, which basically produces amazing results on the benchmarks they care about, which is, I would say it's smart, but it's pretty much overfitting to the benchmarks, and that's why all these models, they are like very much overfitting to the benchmarks, the open benchmarks. Whatever is not in that benchmark, they rarely scale.
Yeah, so we just don't have a broad enough set. To me, it seems like you could overfit to a specific benchmark, but there's a general class. It feels like there's a general class of downstream task that you would like to optimize. But anyhow, I didn't know that, so thanks for raising that. Yeah, I'll definitely take that paper up too. Okay, so that was what it didn't cover. Then the places that it triggered areas of interest for me. They referenced a recurrent transformer, which is interesting because I was kind of interested in the idea of weight sharing within a transformer model. So I want to follow up on that one. The phi, the textbook is all you need one, focusing on dataset quality. This Llama 3.1 now I'll add to this. And then the chinchilla, this is the chinchilla paper. I'd like to go through that a little bit more detail. So that was it for me, I think. I will post this.